Welcome back to our second of 3 videos in discussion of 9.1 on sequences. And so if you remember in the last video, we introduced sequences. We worked a little bit with them with some examples, just kind of reminding ourselves what sequences are, how they work, and also reminding ourselves that we can introduce some new types of operations like alternating things, factorials. We can even get recursive sequences defined. And now what we're going to do is more importantly, talk about the calculus that we can do with sequences. If you remember in the last video, sequences are functions on the natural numbers. If I graph them, they just look like a bunch of dots in the plane. And so things like tangent lines and areas under curves becomes irrelevant when we talk about sequences. However, one thing we did notice about sequences is that they are infinite. If I write out all the terms to a sequence, there is no end. The natural numbers never end. And so I can continue to plug in natural numbers into these sequences, continue to get terms or outputs, and create a list of outputs, starting with the first output, second output, and so on. Now, the question or where calculus comes in is to ask ourselves, well, what happens to the terms of my sequence, the outputs, if I let n, the natural numbers, go off to infinity? What is the last term in the sequence? What are they approaching, if anything at all? Sequences don't have to approach a specific number. Sequences might blow up. If I define my sequence to be a sub n equals n, means if I plug in 1, I get 1. Plug in 2, I get 2. Plug in 3, I get 3. If we look at the outputs there, and I continue to plug in natural numbers, those outputs are just going to blow up to infinity, just like the natural numbers do. So they don't approach anything. But it may happen that I give you a function on the natural numbers, a sequence, where the outputs of those sequence, or the terms, do approach a specific number as n goes off to infinity, as n gets large. And so let's first write out the definition of what do I mean by the limit of a sequence. There's only one limit to take. Notice it's very important. It's not arbitrary to say the limit of a sequence. If we're talking about functions, I have to be specific. I have to say the limit as x approaches c. Because we could approach all sorts of values for continuous functions, because you can approach the curve from either side, approach a specific point. With natural numbers, there's no curve, right? So we can't approach a dot in space continuously. And so we can't take limits of sequences at certain points. The only limit that makes sense to talk about is the limit as n goes off to infinity. So it's not arbitrary to say the limit of a sequence. It's implied that you're letting n go off to infinity. And so what do we mean by the limit of a sequence? Well, given a sequence a sub n, so we have to start with the function on the natural numbers, we say the limit as n goes to infinity of a sub n equals L. So we're saying the outputs of this sequence, the terms, are approaching a specific number as n blows up. What do we mean? The sequence is becoming arbitrarily close to L as n gets larger and larger. What do I mean by that? Explicitly, I mean that for any epsilon greater than 0, right? We've seen this definition before in Calc 1. For any epsilon greater than 0, now it's a little bit different, there exists a natural number, call it capital N. There is some term in this sequence, way out there maybe, so that for all n larger than that n, there's some natural number, so there's a starting point. So once I hit that natural number, from then on, from thereafter, all the outputs of my sequence are going to become that close to L. So the difference between a sub n and L is now less than epsilon. The outputs of my sequence of terms, L being my claimed limit, the difference between them, how close are they to each other, is now that small. And if I can do this for any epsilon, basically the point is as small as you would like, we could then say that the outputs of the sequence are becoming arbitrarily close to L. If I can do this for any epsilon. There's always going to be some point in the sequence where we become that close. And so that's what we mean by the limit of a sequence. Now let's see it worked out in an example, the formal definition, before we get all our shortcuts in. And so let's prove the limit as n goes to infinity of 1 over 3 to the n plus 1 equals 0. Now, I told you the answer, but we can use our intuition to get an educated guess of what we think the answer would be. Remember, this is a function on the natural numbers, and so if we look at the terms of the sequence, a1, that would be plugging 1 in. If I plug in 1, I get 1 over 4, right? 3 times 1, which is 3, plus 1, which is 4. a2 is 1 over 6 plus 1, so 1 over 7. a3, 1 over 9 plus 1, so 1 over 10. a4, 1 over 12 plus 1, 1 over 13. dot, dot, dot. And so if I write out the terms of the sequence, I have 1/4, 1/7, 1/10, 1/13, dot, 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 dot. And based on what I see in the first couple terms, I would think that the terms are getting smaller, right? Bigger denominator means smaller fraction. And it looks like the terms are going to 0. They're getting smaller and smaller, in fact, arbitrarily small and close to 0. So it's not bad to make an educated guess that we think the limit is going to 0. You use your intuition. Well, my intuition might not be great, right? We have to understand that we're only looking at the first 4 or 5 terms. We need to understand what happens as n goes off to infinity. Now, how far away is infinity from the 4th term? Infinitely far away. You understand what infinitely means, you're never going to, it's an infinite distance, you can never cross it. And so to make an educated guess off of 4 terms, that might be correct, but how do we formally show it? Well, then I would need to go to the definition. And so let's see. Given any epsilon greater than 0, given any epsilon greater than 0, let's see if we can find a natural number so that it can become that close, whatever epsilon is. My sequence can become that close to 0 for some natural number. And so let's see. What's my term a sub n? 1/3n plus 1 minus 0. Let's see if we can make the difference between the outputs of my sequence and 0 that epsilon small. So let's see if we can make the difference between the function and my claimed limit epsilon small. Let's see if we can find an n. So we want to solve this for n. We want to see if there's an n so that for any n greater than that number. Of course, that number will depend on epsilon. So my n will depend on epsilon. Let's see if we can figure it out. Let's just manipulate this a little bit. Minusing 0 doesn't actually do anything here. If there was some other number, we'd have to, find a common denominator, subtract some fractions. And so we get this less than epsilon. We understand that sequences are functions on the natural numbers, and so n is positive, starting at 1. So the absolute value actually doesn't mean anything here, so we can actually get rid of it. It's not always true that you can get rid of it, but in this context you can. Let's multiply both sides by 3n plus 1. Now, in general, multiplying both sides of an inequality, you would have to be careful to make sure that this does not switch. And it does not, because remember, n is a natural number, starting at 1. And so the denominator is always positive and getting larger. So it doesn't switch. Distributing the epsilon through, 3n epsilon plus epsilon. And remember, solve this for n. Let's see. So move the epsilon to the other side. Let's divide both sides by 3 epsilon. And sure enough, we're able to find a place. What I've done now is I've manipulated the way that this looks, right? The goal is, hey, the outputs of my sequence and 0. Let's see if we can make the distance between them. This is what this represents on this side. Let's see if we can make the distance between them less than epsilon. Can I find an n where this is true? All I did was some algebra and manipulate this fraction, and sure enough, I did. It turns out that if n is larger than 1 minus epsilon over 3 epsilon, then we are able to do this. So yes, technically I've proved this, right? For any epsilon, given any epsilon, as long as I make n, what term in my sequence, what's my capital N? Well, whatever the next term is here, so that I'm larger than 1 minus epsilon over 3 epsilon. So given any epsilon, I can find an n. And so yes, we are right, the limit is 0. We've technically proved it at this point. But let's just see it worked out. For example, what if epsilon was 0.01? If epsilon was 0.01, then as long as n is larger than whatever this number is, n needs to be larger than 1 minus epsilon over 3 times epsilon, then we would be sure that this statement is true. Well, let's see. 1 minus 0.01, 0.99 over 0.03. So we have 0.99, right? That's 1 minus 0.01. And then 3 times 0.01 or 0.03. And if we take this and put it in a calculator, we get 33. And so what does that mean? That means as long as n, as long as the term in my sequence, the natural number I plug in, is larger than the natural number 33, then the difference between my sequence outputs and 0 will be less than 0.01. Let's see, and so in this case, let's let capital N be 34. As long as n is larger or equal to 34, then we're guaranteed that we are 0.01 away from 0. And so let's see, what would a sum 34 be? That'd be 1 over 3 times 34 plus 1. And if I put that in a calculator, and I do 3 times 34, which is 102, plus 1 is 103, and then I take the reciprocal of that, or 1 over that, I get 0.0097, ... Well, how close is this number that I just found away from 0? Well, I'm subtracting 0, doesn't mean anything. So 1 over 3 times 34 plus 1 minus 0, the value of that, well, that's 0.0097 ... And sure enough, that is less than 0.01. And so we found a place, right? We found a natural number so that for all n larger than that natural number, we become that epsilon close. Now, I did it for a specific epsilon. That's not what the goal was. The goal was to prove it in general. That's done here, right? We're able to do it. Given any epsilon, I can find an n. As long as n is larger than that number, you're in good shape. I did it now for this specific one. So say epsilon was 0.01, you can do it. That means in this case, n would need to be at least 34. We need to go to at least the 34th term to be 0.01 away from 0. So actually not even that far. Right? This goes to 0 pretty fast. Now, of course, proving this with limits every single time, we don't like the limit definition in general in calculus. We use it, to get our idea of what a limit represents. But then we love shortcuts, right? We like to get the idea of, okay, how can I evaluate limits of sequences without having to go through this whole epsilon and n thing every time? And of course, there are shortcuts to this. So we're going to move over to the other board, and we're going to look at using calculus now, or some other techniques of calculus we've learned, in order to help us evaluate certain types of limits of sequences. And so just as an important piece of information or facts to remember, if we ever encounter 1 over n as n goes to infinity, right, if the bottom of a fraction blows up, 1 over n, 1 over infinity, that's going to 0. You don't need to prove that. 1 over n goes to 0. In fact, I proved 1 over 3n plus 1 goes to 0. But a general fact, 1 over n, as n goes off to infinity, is going to 0. And in fact, in general, any constant over any power of n will go to 0, as long as r is positive. Why do I need it to be a positive power? Well, that guarantees that n actually stays in the denominator. If r was negative, that would be bad because now n is in the numerator, and this thing would possibly blow up. So we don't want that, so we'll make sure n stays in the denominator, and as long as that's true, then this will also go to 0. All right, so just some facts to remember. And how are we going to use calculus? We're going to look at 2 different things we can do. The first one is to model an by a continuous function, f of x, on 1 to infinity, where f of n equals a sub n. What do I mean by that? I mean, it's a fancy way of saying connect the dots. If I can connect the dots of the sequence by a continuous function, f of x, right? If there's some function that agrees with my sequence everywhere and plays connect the dots with them, then I could use everything from calculus at that point. Because then at that point, wherever f of x goes, so will this sequence. So model a sub n by a continuous function f of x, where f of n equals a sub n. What's the point of this? Then the limit as x goes to infinity of f of x will agree with the limit as n goes to infinity of a sub n. That's the whole point of doing this. And why do I care to do the continuous thing? Is because now everything we know from calculus. Specifically, there's ways to talk about infinite limits in calculus, right? We talked briefly before the start of chapter 9 about indeterminate forms in L'Hopital's rule. And so let's look at an example where modeling by a continuous function might be useful to us. And so what if we were given this sequence? A sub n equals ln of n over n squared. And say I wanted to know what is the limit of this sequence. So find the limit as n goes to infinity of a sub n. So we would want the limit as n goes to infinity of ln of n over n squared. Now trying to do the whole epsilon and delta thing might be a little bit challenging because of the ln of n thing, right? Solving for n and using the exponentials, that might be a little bit confusing. You might be able to do it, but let's try to avoid that. And let's play connect the dots. Now, while it seems fun to try to play connect the dots, there's really no thought necessarily that goes into this. It's basically asking yourselves, if I replace n with x, is that okay to do with numbers besides natural numbers? So if I just think of now f of x equals ln of x over x squared, is there anything wrong with that from 1 to infinity? Do I have any discontinuities or any issues with this function on 1 to infinity if I replace n with x? And in fact, I don't. Putting this in the denominator, we're never going to divide by 0 because we're going from 1 to infinity, we're good. ln is continuous on 0 to infinity, so we're good from 1 to infinity. And so there's no issue with this function on 1 to infinity, no problems. And so this will play connect the dots. Now what we can do is say, okay, well, let's just answer the question about the continuous function. What would be the limit as x goes to infinity? And now things we learned from calculus come into play because now we're dealing with continuous functions on 1 to infinity. All real numbers on 1 to infinity. And so ln of x over x squared, if x goes off to infinity, well, we see the denominator is definitely going to blow up to infinity. The numerator, if you're unsure of ln of x, just look at a graph of it for a second. Well, technically it is. It's the inverse of an exponential, but it still grows. It looks something like this, shoots up, and it will also blow up to infinity. Why is that a good thing? Well, infinity over infinity, remember, is not 1 necessarily. Infinity over infinity is what we call an indeterminate form. Indeterminate form. This is what we talked about in L'Hopital's rule. And specifically, this is a type of indeterminate form I can address using L'Hopital's rule. And what does L'Hopital's rule say? It says, well, if you have an indeterminate form of infinity over infinity or 0 over 0, then this limit is equal to the same limit with the ratio of their derivatives. Now, why is it important that I use continuous functions? Because now derivatives actually exist. I have continuous functions, I have tangent lines, I have slopes. Derivatives are okay to take. I can't take the derivative of this. This is just a bunch of dots in the plane. I can take the derivatives of these functions. Now remember, L'Hopital's rule is the ratio of the derivatives of the numerator and denominator respectively, meaning I'm not using the quotient rule here. It's just the derivative of the numerator, which is 1 over x, the derivative of the denominator, which is 2x. Let's simplify this since I have a fraction within a fraction. So limit as x goes to infinity. Now that's 1 over 2x squared. Well, that's great because now that's the limit as x goes to infinity. Now I have a constant over some power of x. Remember this general fact, right? And this also includes x. This is going to go to 0. 1 over infinity, right? The numerator is now fixed. This is not indeterminate. 1 over infinity, a constant over infinity, that's getting arbitrarily small. In fact, it's going to 0. And so what can we say about the sequence then? Well, the limit of the sequence would also be 0 because it's glued onto this function, and this function goes to 0. Why did I like the ability to use a function? Is because in this case, L'Hopital's rule helped me. And L'Hopital's rule only applies to functions in which you can take derivatives of continuous functions. And that's why this works. And so one aspect or one shortcut we can use is being able to model a function by, or model a sequence by a continuous function, and therefore being able to use anything we know from calculus. Specifically, maybe L'Hopital's rule might be useful. Something we talked about right before this chapter. Well, what if it wasn't like this? What if it was something maybe I couldn't model by a continuous function? Say my sequence looked like this. Say instead of ln of n over n squared, now it was negative 1 to the n over n squared. And we still have the question, find the limit as n goes to infinity of a sub n. So we'd want the limit as n goes to infinity. We want to see what happens to the outputs of this function as n goes to infinity, negative 1 to the n over n squared. What does it equal? Well, in this case, modeling it by continuous function, asking ourselves, hey, can I just do this? Can I replace n with x on 1 to infinity? X squared. Is this okay? Absolutely not, though, now. Because on 1 to infinity, all real numbers from 1 to infinity, that includes a lot of fractions. And in fact, any fraction with an even denominator would require you to take an even root of negative 1, which does not exist, right? It's not well, it exists, it's just not a real number. And so I can't do this like I did here. That's not okay. And so what else could I possibly use? Well, I could use something else that I also learned from calculus, specifically Cap 1. And that is what we call the squeeze theorem. Squeeze theorem applied to functions, but we can also apply it to sequences in the same way. Given sequences A sub n, B sub n, and C sub n, so 3 sequences, so that they follow this sort of structure. We have B sub n less than or equal to A sub n less than or equal to C sub n for all n, right? A sub n is sandwiched between these two sequences. It's bounded between B sub n and C sub n. And say we know the limits of the outer sequences, right? The things that are bounding A sub n. And say B sub n and C sub n, both of those limits go to the same place. I can answer those, and they both go to L. Well, if you think about what this means now, A sub n is stuck in between them. B sub n and C sub n become arbitrarily close to L. Both of them do. A sub n is stuck between them, and so it must also go to L. Right? That's the conclusion of the squeeze theorem, if you remember from Cap 1. And so say maybe you don't know A sub n, you don't know the limit of A sub n, but you can bound it between two sequences that you do understand, and both of those sequences go to the same place, then the one in between them, the thing you don't know, would also have to go to the same place. How do I use that here? Well, let's think. Negative 1 to the n over n squared. I can bound this between two things that I actually do understand in terms of limits. Remember in the last video we talked about what negative 1 to the n does. It doesn't contribute to the value of this number, it just changes the sign of this number. And so this sequence is always bigger than or equal to, well, negative 1 over n squared. Worst case scenario, it's negative 1 over n squared, so it's either equal to this side, or if n is even, it's equal to this side. So no matter what you do, no matter what value of n you plug in, it's bigger than or equal to negative 1 over n squared. In fact, it's equal to it if it's an odd power. And certainly it's less than or equal to 1 over n squared. In fact, it's equal to it if n is even. So it's not an actually interesting one because you're not actually technically stuck strictly between them. You're either one or the other. But this is useful to me because look at both of these sequences on either side. And let's enter these. Well, both of these are the forms, some constant over a power of n. Well, that power is positive and that constant doesn't matter. Both of these are going to go to 0. The one we're unsure of is stuck in between both of these, and the squeeze theorem then says, well, the one in between has no option. It must go also to whatever these sequences went to. In this case, they both went to 0, and so what does that mean for me? That means the limit as n goes to infinity of negative 1 to the n over n squared must also equal 0. I didn't use the continuous function route, I used the squeeze theorem route. Going about it. So squeeze theorem or modeling by continuous function. In the same way, right, say we have, let's do one more example. Say we have n factorial over n plus 2 factorial. So n factorial over n plus 2 factorial. Well, I don't really like to work with factorials by themselves. Or can't model them by a continuous function as it's written. Factorials don't exist for real numbers, just natural numbers, so I can't do the whole f of x equals thing. Trying to squeeze it between two things becomes a little bit harder to think about. This is easier because the negative one end just switches signs, so it's a nice, easy way to think about bounding them between two things. And so before I do this, let's maybe simplify this expression. Let's realize that since I have a factorial over a factorial, maybe I can reduce something and make this look a little bit better. And in fact, we can. The numerator is 1 times 2 out to n. N plus 2 factorial is, well, that's still 1 times 2 times 3. It's still going out to n. In fact, it's going even farther. It's going to n plus 2. And so there's n plus 1 times n plus 2. That is where I would stop. So if this stopped at 7, then this one would stop at 9, right? 7, 8, 9. 7 factorial over 9 factorial for A7, and so on. And so I write out just what these factorials are defined to be, and I see that we have lots of reduction. In fact, everything up until n will cancel. The only thing left in the numerator is 1, reduces to 1. And what's left in the denominator is just a product of n plus 1 times n plus 2. If you want to FOIL it out, you can, right? You don't have to, but we get n squared plus 3n plus 2. And so actually a sub n can be rewritten in this way. Now that I've rewritten it like this, now there actually is nothing wrong with rewriting this as f of x. There's nothing wrong here. There's no issue with modeling it by a continuous function. This is just a polynomial. This is okay to do. There's no domain issues on 1 to infinity. And so that means I can now answer the question, what happens as x goes to infinity for this continuous function on 1 to infinity. And wherever this function goes, that's where the sequence will go as well, because it's glued onto it. And so if we look here, 1 over x, as x goes out to infinity, this is a quadratic. This is blowing up, right? Infinity squared, 3 times infinity plus 2. We're going to get 1 over infinity. That's not indeterminate, right? We're not using L'Hopital's rule here. That would be if it was infinity over infinity. But the numerator is fixed, it's constant. And a constant over infinity, that doesn't blow up, that goes to 0. And so what does that mean? That means that this expression is going 0. Limit as n goes to infinity of n factorial over n plus 2 factorial, this equals 0. I do this example to bring up the idea that, okay, if I have factorials present, it may be useful sometimes to reduce it. If I have factorials and other factorials combined, divided in some way, maybe reduce it, might make it look a little bit easier, and then we can either maybe use a continuous function and use what we know from calculus, maybe L'Hopital's rule, or maybe the squeeze theorem as well. So these are different aspects of evaluate. Of course, the standard definition or the formal definition as well. So we have the formal definition of the limit, the whole epsilon thing, and we have some shortcuts as well. These are some ways in which we can evaluate limits of sequences, answering the question, what happens as n goes off to infinity? And so now that we've done this, in the next video, the last one, the third video in 9.1, we're going to look at some special properties. So we're not done with sequences yet. We're still going to talk one more time briefly. And we're going to introduce just some special properties sequences can have. We're going to introduce the property of being what we call monotonic and the property of what we call being bounded, and what both of those properties imply or tell us about a sequence. So in the last video in 9.1, we'll introduce some special properties of sequences that may be useful later, and then we'll move on to series.